first it's important to say who we are and what we do. I'm working within the Bouygues group. It's I believe, the fourth biggest building and construction company in the world. I'm working within the engineering division of their French real estate branch, within a research unit whose purpose it is to adapt the production of the company to emerging challenges. Three of them being the fact that we're going to need to build stuff that lasts much longer than what we're used to. The main reason for that being that we know for a fact that construction activity within the EU market is almost linearly indexed to the EU supply of oil. Oil is the factor in everything that we do, and along with this decrease in projected supplies, it's bound to decrease by a factor of 2 to 10 in the next 25 years. We're going to lose our capacity to adapt to climate change. And so we need to build buildings which are going to last hundreds, if not thousands of years. Obviously, one of the second biggest challenges that we're facing today is that we have to emit a lot less than what we're used to. When it comes to the French context in which we're working, this has a lot more to do with embodied emissions than operational emissions. The reason being that we have very unlike in the UK, very strict thresholds that we need to respect in terms of both operational and embodied emissions. And within the buildings that we're delivering today, it's about more or less than 92% to 8% ratio when you compare embodied to operational emissions. So the big challenge is in reducing the embodied emissions of the manufacturing of the construction materials that we use. And obviously, the last challenge that we're mostly interested with today is to cool passively the buildings that we provide. The reason for that being that the increase in summer temperatures, especially within the French context, have proved to be a massive public health challenge at the moment. The 15,000 deaths in France associated with the 2003 heat wave are going to be what we could refer to as a very chill summer in 2050. And we have seen that mechanical cooling wasn't a right answer to this challenge, mostly because it's counterproductive from many different perspectives. It amplifies the urban heat island effect of about 2 degrees within French city centers due to the exhaust first exhaust of the heat outside of the building due to refrigerant leakage and the greenhouse gas effects associated with it, and also the escalating contribution of the operational emissions used for the operation of those equipments. It has proved to be pretty unfair, socially speaking. There's actually a high price associated with purchasing such an equipment and running it. Within the French context, upper income households have a much bigger access to mechanical cooling equipment than lower income households, and it has proved to be and becoming more and more unreliable during heat waves, which happen to be drought and high pressure compound events. So they put quite a high pressure on the electricity production system of the French grid, especially when we talk about nuclear power production. The thermal discharges within the rivers force the lowering of the production capacity. We don't have any wind power during a high pressure event, and the drought associated with it reduces or puts constraints on the hydroelectric production. So when you need electricity the most to cool yourself, you actually happen not to have it, and maybe not to have it even more in the future. So when we take those three challenges together, cooling passively, emitting less, and lasting longer, it actually has a lot to do with how we used to build stuff before fossil fuels were around. And what we're really interested in the lab are high thermal mass buildings, especially built with natural, non-transferred geosourced materials, and their capacity to emit less, last longer, and passively cool buildings. It's been proven within the literature that high thermal mass buildings actually help to emit less across the entire value chain of the building, because the monomaterial assemblies that we use accumulate a certain amount of functions that allow us to reduce the material inventory of the buildings and the associated embodied emissions. It also has less and limited embodied emissions due to the fact that those materials, if just taken out of a quarry or out of the site, tend not to have a lot of embodied impact because they have been produced millions of years ago and we're just moving them from the quarry to the building site. They tend to last much longer, obviously, because weight induces permanence, whereas lightness in all the current ways and practices that we're using only induces short-lived products. And obviously, through the work of the thermal mass associated with it, you can passively cool people. So most of the work that we're doing has to do with implementing the use of high thermal mass and masonry buildings on a large scale, which has to be included into the planning of industrial ecology roadmaps, which relies on the backing of the public sector, most importantly. And the urgency of the problem requires us to bring forward a certain amount of quantitative and large-scale macro analysis so that we can know for sure that what we're proposing has benefits in terms of climate adaptation and mitigation. It's within the current literature, trying to prove that geosourced materials emit less is pretty easy because we have material and carbon flow analysis at the macro scale to do that. Trying to prove that they last longer is a no-brainer because you can just look at the existing building stock. But trying to show on a systemic scale that they could passively cool people in the future and providing quantitative analysis that can tend to demonstrate that is a much harder thing to do. So when we talk about quantitative analysis of the applicability of passive cooling methods at the macro scale, what we mean is to what extent can passive cooling technique meet the temperature demand for comfort and safety in current and future climates at the national scale, at the global, and well, in the study that we're putting together at the EU scale. And by the way, the study is very much a refinement of an earlier study that Richard helped us put out there 2 years ago. So thank you to you, Richard, again. The why it is currently missing has been largely covered by Daniel in his press just a few moments back. It has a lot to do with the fact that it's super complicated to perform those types of analysis at the macro scale. What usually gets done in current climates is that you take a building model, you put it in an energy simulation software like Energy Plus, you input current climate data or historical climate data within the simulation software. You run the software, you study the results, obviously, but the results are extremely hard to get because it's computing intensive, it's time intensive, and it's money intensive, and it happens to be only site specific and climate specific to a specific location. So what people have done within the literature up till now is that if you wanted to get a macro scale idea of the future performance of passive cooling methods, you needed to simply repeat that with constant return rates. And it was, the more you wanted to do it, the more time it took, the more computing power was necessary for the thing. And you had to extrapolate the fact that maybe the site that you had selected was representative of a larger zone, which happens to have a lot of limitations as well. So when people tried to do that for future climates, they encountered all the problems that you cited, which first meant that they would need to convert future projections to daily and hourly climate data that they could use within the same simulation softwares. And it came with all the same limits. So what we've been trying to do is to tackle those limits. The first one being that it's extremely time and computing intensive, and it doesn't harness the full potential of global climate models and regional climate models, namely the fact that those models provide climate data on a gridded system. So you're just using one specific location of the system and then extrapolating for the surrounding environment. So what we're doing is that we're performing all the computations within the GCM and RCM data sets. Immediately, it's very short, it's not computing intensive, and it provides a macro scale view of what's actually happening without having to rely on one specific site. The method that we're using, so I said it was gridded, but it's actually three-dimensional data, the Z dimension being the time. So if you take just one square, the coarse resolution obviously is just for the purpose of the presentation. It's a much better resolution within the RCMs that we're using. For one specific day, we're extracting a few climate variables like the mean temperature and the max temperature. We're deriving, assuming harmonic variation throughout the day. 3 minutes left. All right, cool. I'll try to make it as fast as I can. But so what we're doing basically, I'll jump a bit. I was thanking you, Sue, for the and Fergus Nicol in the room for the development of passive cooling standards. But what we're saying, I'll just quickly go there. What we're doing is that we're extrapolating the diurnal temperature variation within each and every site, and then we're studying three separate scenarios. The first one being a high thermal mass building. Second one being a low internal thermal mass building, well ventilated, and the third one being a low internal thermal mass building, poorly ventilated, so with an overheating risk. And we're computing the cooling degree hours above the adaptive comfort threshold for an extrapolation of the temperature need for comfort and the temperature need for safety. We're using the heat index. I didn't know about the SCT that you just presented, but that would be very interesting to put in the model. So in any case, we can extrapolate the cooling degree hours above the safety threshold in each and every case, and the cooling degree hours for comfort. With that, we're repeating the array of computation through 20 years period for different time period, different climate projections, and we're extrapolating the energy consumption, operational energy consumption associated with it, and the indirect emissions associated with the energy consumption. So the results, which will soon get out at the EU scale, show, so this is for current climates. We'll just jump to the end of the century. But within the three scenarios, you can see that the high thermal mass buildings on the left allow you to drastically reduce the temperature demand. This is for comfort at the moment on the screen. There's well, you know what? I won't get into the weeds of the details because we don't have much time. But the purpose being to show that high thermal mass and nocturnal ventilation have, well, there's solid evidence that it will be able to keep people comfortable within future climates. This is, by the way, the RCP 8.5 scenario. I wanted to show the most extreme cases, knowing that if you can do the least, you can do the most. No, that's the opposite way around. If you can do most, you can do the least. In any case, jumping to, I won't again get into the weeds of the detail. Just saying that we must ask the question that you asked me, namely being whether or not the discomfort that people will experience in low thermal mass building, will it be a safety concern as well, and in terms of associated relative humidity levels. So we're doing the same computations with the heat index to show the amount of cooling degree days above the temperature threshold for safety. This is at the end of the century again, and we're showing that high thermal mass and nocturnal convective cooling has the ability to meet 100% of the demand for safety within the French context, regardless of the emission scenario that we're considering or the time period that we're considering. Again, I'm not necessarily getting in the weeds of the detail. Just saying that it's the heat index that we're using the extreme caution level, so it's about 30.5 degrees Celsius of apparent temperature, and it's warning of heat strokes, heat cramps, and heat exhaustion during prolonged exposure to the conditions that we're talking about. It's actually interesting to see that if we plot the average number of hours during which those safety levels are surpassed within buildings, it's always more than 5 hours a day that they tend to be crossed. And so when you put that into the perspective of the ability of thermal mass to keep people safe and below those thresholds, it gets pretty interesting. So again, you can convert that to energy use for space cooling. We're using models, this is at the end of the century, but we're using models that embed in themselves the threshold that prompts people to invest and operate cooling equipment. And we've proven that the building high thermal mass building has the ability to retard the investment, just to delay the investment of within, how do you say that? Delay the requirement for AC equipment and installation, which is interesting to put it when we look at the current recommendations. I'll switch pretty fast, but when we look at what's required from the current environmental regulations in France, which is putting a maximum threshold of 70 kilowatts per hour per square meters per year within new construction, you see that cooling requirements within the southern parts of France will almost fully meet that threshold just for the cooling requirements of buildings. And so in that regard, high thermal mass and passive cooling has the ability to greatly help in the meeting of those imposed thresholds. Obviously, you can convert that to the carbon equivalent of the operational emissions linked to space cooling. This would greatly vary between the various countries that we put in the model, but we don't have much problem with operational emissions in France. So it was just to show that we could actually do that, even if the associated emissions with the cooling gains are not that great in the French context. Again, not getting in the weeds of the details. But the conclusions being that high thermal mass and nocturnal convective cooling can meet and will be able to meet 99% of the temperature demand for comfort in France for any location within current and future climates, and regardless, again, of the emission scenario considered. It will be able to meet 100% of the temperature demand for safety within a climate which is increasingly dominated by cooling requirements. We're slowly getting out of the heating-dominated climate that we're currently within. And this can contribute, among many other different things, to a substantial decrease in operational and energy consumption for space cooling, along with carbon emissions. That's it.